Hi everyone, so lesson 1.1 is going to build off of what we talked about in our review, what you took in your first business math, and we're going to talk about compound interest. Now this is one of the foundational components that you need to understand and be comfortable with to be successful in this course. Okay, there's going to be a large quantity of this course relies on this principle of compound interest. And it differs a lot from what we talked about previously, which was simple interest. So simple interest is earned only on the original money you invested. So if you invested $5,000, our simple interest formula, remember it was S equals P times 1 plus RT, okay, where S was also known as the future value, or FV. You only earned interest on that $5,000. Okay? Compound interest is very different than that. And what it looks at is actually what the real life scenario is if you have a savings account or if you have items like that. Okay? So in a savings account, you earn interest on the money you invested in that savings account and the interest that you accumulated. So if you have $5,000 in your savings account and you earn $50 on that in your first month, your total amount is $5,050. The next month, you would earn interest on $5,050. So maybe the next month, you would earn $50.50. Okay, meaning that the month after that, adding those up, you have $5,100.50, and it continues to accumulate that way. Okay, so that is how it works with traditional savings accounts that you're going to see at banks. It's compound interest. So you might ask, why do we teach simple interest? Well, it's because compound interest has many different formulas and variations to it. So understanding the basic principle of simple interest is very important before we move into this more complicated concept. Okay? Before we do that, one more item to note is, remember, in simple interest, we were given a nominal interest rate, and that was given as per annum, okay, or PA. That meant yearly. In compound interest, we're going to talk about the periodic rate. Okay, and what that means in simple terms is we're going to take this nominal rate and we have to convert it to a periodic rate, which is an interest rate per period we talk about. Okay, and you'll see what that means when we talk about compounding periods with compound interest. So I just want to show you a comparison. Okay, now this is a table. It was generated based on the exact same initial investment, which is $10,000, and our interest rate of 10%. Okay, and it was 10%, remember, per annum, which you could see as PA, or yearly. And this money was invested for 5 years. So if we do a simple interest formula, every year we would earn 10%, okay, of our initial investment, which is $10,000. So every single year we would earn $1,000 in interest. So over 5 years, if you add these up, you get a total amount at the end of 5 years of $15,000. With compound interest, remember, we earn interest on the initial amount, our principal of $10,000, plus interest on the previous interest we've earned. So in the first year, in compound interest, you earn the exact same amount, 10% of your initial investment. And that's because you have no interest in your account. So you would earn $1,000, meaning your balance is $11,000. And that matches our simple interest calculation, again, because we don't have any additional interest in the account. Your second year, okay, you have $11,000 in the account. So you would earn 10% times $11,000, or in this case, $1,100 in interest, okay, versus the $1,000. Continuing that, okay, year over year, you'd come out with a total of $16,105.10 compared to just $15,000 with simple interest. Okay, that's $1,105.10 difference. That's substantial, okay, over multiple years. And that actually means that you would earn more money, okay, it accumulates faster with compound interest, which is the method that is used with traditional savings accounts in banks. Okay, so I want to compare what the formulas are so you can see the difference between simple interest and compound interest. So simple interest, okay, if we look at our future value, we always had S, okay, which was, remember, the sum. In this case, you can also write it as FV for future value. And it was equal to your principal times 1 plus your interest rate times your time period. Remembering that your interest rate and time period had to be in the same period in time. And oftentimes your interest rate was provided yearly. So your time period was always expressed in years. Okay, so remember if you had something like 27 weeks, okay, you had to convert that to years by dividing by 52, since there's 52 weeks in a year. Compound interest works differently, okay? If you want to talk using S, okay, our S, or sum, or you can also see it written as the future value, is equal to our present value, the amount of money that you currently have in the account, okay? Because remember, you're earning interest on your principal and on the previous interest you've earned, okay? So it doesn't necessarily have to be the principal. It's equal to your present value times 1 plus I. I, in this case, is your interest rate. And that is raised to an exponent, n, where n is your number of compounding periods. Okay, so I and n are different than our interest rate and our time period because they look at how often you're earning interest. So this formula is going to start introducing different complexities, such as if you earn interest every month, okay, every day, every week, maybe you earn interest twice a year or semi-annually. This compound interest formula allows you to take all of that into consideration. The simple interest formula always just looked at one interest calculation, typically per year. Okay, so that is going to be the big difference here. And I don't expect you to memorize these formulas. So I'm showing you this. You may be writing it down beside you, okay, just to have with you. Alternatively, you can come back to these slides if you print these slides out. Or you can look on LMS and print out the formula sheet. But it will be important for compound interest that you have the formulas available to you. Okay, because as we start getting more into it, the formulas start getting a little bit more complicated. Okay, so now I want to show you what the difference is between the interest rate, which remember was I, okay, in this formula, compared to our simple interest formula. Remember, our simple interest formula, okay, our future value, or our sum, is equal to our principal times 1 plus RT. R was your interest rate per year. In this case, our interest rate is I, and what it represents is the interest rate per period. So the actual formula is what we call J, which is our nominal interest rate. In other words, the interest rate as yearly, divided by our number of compounding periods per year. So if your question was given as your interest rate is 5% per annum, compounded monthly, okay, just as an example of how this is provided, You would have your nominal interest rate, J, is 5%. Remember, converting that to a decimal, for every single formula, you have to convert to a decimal. So that does not change from our simple interest to our compound interest formula. So converting this to a decimal, it's 5 divided by 100, removing the percentage sign, which is 0.05. When we write compounded monthly, our term M here, which is the number of compounding periods per year. Okay, so every month you're going to earn a little bit of interest, meaning that your compounding periods M would actually be equal to 12, because 12 times a year you're going to have interest calculated. Okay, that's what it means by compounded monthly. So what this does is we calculate an equivalent interest rate, looking at every single month, we're going to earn a little bit of interest, okay, with our total yearly rate being 5%. So in this case, our periodic interest rate, which is I, okay, per period, would be equal to our nominal interest rate, 0.05, divided by our number of compounding periods per year, which is 12. If we put that in our calculator, we actually would get a repeating decimal, 0.00416 as a repeating decimal. Okay, so you see that number is much smaller than the 5% or 0.05 we started with. And that's because you don't earn 5% every single period. You earn little bits of interest throughout the year, okay, that work out to our overall interest rate for the year of 5%. Okay, it actually works out to a little more than that, again, because remember, in compound interest, you're earning interest, okay, on the previous interest you've earned. Okay, so just to nail these concepts, let's look at an example trying to put all these pieces of the new formula together. For a sum of money invested at 4.2% compounded semi-annually for 5.5 years, determine A, the nominal rate of interest, B, the number of compounding periods per year, and C, the periodic rate of interest. So for part A, we're looking for the nominal rate of interest. And remember, that's given in the question usually, okay? And it's usually the interest rate that's yearly. Okay, so in our question here, we're given that it's invested at 4.2% and it tells you how often it's compounded. Okay, so that is giving you a hint. This, in the question, is the nominal rate of interest, okay, and it hasn't been converted to a periodic rate yet. So remember, our formula is I is equal to J divided by M, where I is the periodic rate of interest. J is your nominal rate of interest. And M is your number, that's a bad number sign, number of compounding periods. But this is per year, okay? We're going to get into the total number of compounding periods, which is called N, next. So what we have in this question is for part A, we're looking for J. For part B, we're looking for M. And for part C, we're trying to put it all together and find I. So like I said, in the question, it's giving you the interest rate and telling you how often it's compounded. That's telling you that that's the nominal rate of interest. So we're given that the nominal rate of interest is actually 4.2%. Okay, and since we're just looking for that rate, we don't necessarily have to convert it to a decimal. But if we look down to part C, where we're looking for the periodic rate of interest, it's clear that we have to do a calculation because we're looking for I here, okay, which is a combination of the nominal interest rate divided by the number of compounding periods. So I will also convert that to a decimal, which remember is 4.2 divided by 100, removing the percentage sign, which is 0.042. For part B, we're looking for the number of compounding periods per year. Now, you see another number in this question, 5.5 years, but that's your total time frame. That's not the number of compounding periods per year. What you're given in the question is that it's compounded semi-annually. Okay, so that means that 2 times per year you're calculating interest. So that means for B, your number of compounding periods, which is M, is simply equal to 2. Okay, so the 5.5 years does not come into consideration for this calculation. It comes into consideration for a different one that we're going to talk about next. For part C, we're looking for our periodic rate of interest, and now that we know both the nominal rate of interest and the number of compounding periods per year, it's just a simple calculation. So our periodic rate of interest, I, is equal to J divided by M, which is 0.042 divided by 2, or 0.021. Okay. Now remember, converting a decimal to a percentage in your solution, if you'd like to list it as a percentage, you simply multiply by 100% and you get 2.1%. In other words, it's half of what our nominal interest rate is, and that's because it's compounded 2 times a year. Okay, so you earn half that interest in your first 6 months and the other half of the interest in the second 6 months. Okay. All right, so let's look at a different question. Okay, again, looking for the same concepts here. For $7,500 invested at 7%, compounded monthly for 5.5 years, determine A, the nominal rate of interest, B, the number of compounding periods per year, and C, the periodic rate of interest. So once again, we're looking here for just a couple calculations. So there's a lot of data in this question that we would use, in future types of questions, okay, when we're putting everything together, but it's not relevant when we're just finding these types of interest rates. So remember, we'll start with our formula. Our periodic rate of interest is equal to our nominal rate of interest, J, divided by our number of compounding periods per year, M. So for part A, we're looking for J, which is the nominal rate of interest. That again is provided in our question as 7%. Okay, so we simply know that our nominal rate of interest is 7%. If you want to convert that to a decimal, it's 7 divided by 100, removing the percentage sign, which is 0.07. For part B, we're looking for our number of compounding periods per year. Okay, again, it's given in the question that's compounded monthly. Okay, there's 12 months in a year, so our number of compounding periods per year is 12. Okay, you can see we're not using the amount that you invested, and we're not using your total number of years it was invested. Okay, that comes later on when we start putting all of these pieces of the puzzle together. For part C, okay, we're simply finding the periodic rate of interest, which is our nominal rate of interest divided by our number of compounding periods per year, both numbers that we previously found. Substituting those in, 0.07 divided by 12, which gives us 0.00583, again as a repeating decimal. And if you want to convert that to a percentage, you simply multiply by 100%, and you get 0.583%. Okay, you can write it as a repeating decimal if you like. Okay. Our last item to talk about is determining the number of compounding periods. Now this is the total number of compounding periods for the investment that we're talking about. So previously, you saw our formula, we had I is equal to J over M, okay, where we were trying to find our periodic interest rate. M here was our number of compounding periods for 1 year, okay, so periods per year. N instead is the total number. So if you invest for 10 years, you multiply your number of compounding periods per year by 10. Okay, so putting that plain and simple, for our formula, n is equal to the number of years in your term multiplied by this term m that we've talked about. Remember, m is the number of compounding periods per year. So like I noted up here, okay, if you have an investment for 3 years and you're compounding monthly or 12 times a year, your value for n is 3 years times 12 compounding periods per year, giving us a value of 36. Okay, so let's look at just one more example, just so you can get the feel for calculating this total number of compounding periods term. Ben invested $1,000 at 9% compounded monthly for 2 years. Determine the number of compounding periods n. Okay, so this time, remember when we did the calculations for m, the number of compounding periods per year, we didn't care about how long the investment was. We only cared about this first piece here where it said it was compounded monthly. Now, when we're looking at the value n, okay, we start to look at both pieces of data, okay, because we need to understand how often it's compounded in 1 year, as well as how long your term is for your investment. So in this case, it's compounded monthly, meaning our value for m is 12, and our investment period is 2 years. So our value for our number of compounding periods n, remember, is equal to the number of years in the term multiplied by our value of m. So if I substitute these in, I have 2 years times 12 compounding periods per year, since it's monthly, gives us a value of 24. Okay, so that was our last piece of the puzzle, and we start to talk about these compound interest formulas. So let's put it all together now. Okay, so we're going to talk about this formula. I show it 2 different ways. Okay, they're the exact same formula here, but one is using the terms that you'll see in your textbook interchangeably in this chapter. And then I've also used terms that I just find make it more familiar to you. Okay, so our formula, written as the way it was in the textbook, S is equal to P times 1 plus I all to the exponent n. I here is the interest rate per period, also known as the periodic interest rate. N is our total number of compounding periods for the entire term of the investment. P is known as our principal, okay, or initial investment. The other term you see used for that is present value. How much value was invested today, okay, to amass a certain value in the future. S is known as the sum, okay, multiplying them all together. I like using the term FV for future value, okay? So the second way to see this formula, again, these are the same formulas, is that your future value is equal to your present value times 1 plus the periodic interest rate, I, raised to the exponent n. I'd like it that way because it says you're starting off with a value of money today, your present value, and it's going to be invested and you're going to earn interest, and it's going to come out as a future value in a certain number of years, okay, whether that's 1 year, 2 years, 10 years, okay. So this is the way that you will see formulas written by me, okay, moving forward. I just like to show you both ways, and I want you to understand that it is the same formula, okay. The last item that we'll talk about here is our periodic interest rate. If you remember, that's equal to your nominal interest rate, which is normally given yearly, okay? You might often see it as per annum in a question, or P dot A, okay, which is just the short form for per annum. So that's equal to, again, your nominal interest rate divided by your number of compounding periods per year. Okay, it's important for you to know that this calculation is for per year, and your calculation for n, okay, is for the entire investment. Okay, it's a subtle kind of distinction, but it is one that I see a lot of students make a mistake on. Okay, so keep that in mind when you're looking at these questions. So let's look at a question where we put all of this together. A debt of $8,000 is payable in 7 years and 5 months. Determine the future value if the interest rate is 10.8% PA or per annum, compounded annually. So in this question, now that we're actually looking at a future value calculation, we have to take into account everything that's written in this question. So what I like to do, and you saw me do it in previous questions, is I like to have a little sidebar on the right where I can find all the terms I need to use to substitute into our final equation. Okay, so we're asking us to find the future value. So it's asking us for FV. So if you remember, our formula for future value was equal to our present value times 1 plus our periodic interest rate raised to the exponent n, which is our total number of compounding periods. So we need to find our present value, our periodic interest rate, and our total number of compounding periods. So again, I like to have a sidebar here on the right. We don't know what our future value is, but we do know our present value, okay, because it's saying it's a debt of $8,000. Okay, we have to pay it off in 7 years and 5 months. So that's the value of it today. But remember, with debt, okay, whether it's a student loan or a line of credit or anything, the longer you take to pay the debt off, the more that debt will cost to pay, right? And that's because the bank or whoever's loaning you the money collects interest on it. So our present value today, if we paid this loan off right now, would be $8,000. But we're not paying it off, okay? We're looking way down the road, 7 years and 5 months from now. So we have our present value. Let's look at our periodic interest rate. So our periodic interest rate is equal to our nominal interest rate divided by M. Okay? Our nominal interest rate is usually given in the question. In this case, it's given as 10.8%. So it's 10.8%. Again, remember, you have to convert this to a decimal to use it in your formula. So you take 10.8. Sorry, I put a decimal there I shouldn't have. 10.8 divided by 100, removing the percentage sign, which is 0.108. And our number of compounding periods per year, it's given that it's compounded annually. Okay, annually meaning once per year. So our value for M is 1. So now we can calculate our periodic interest rate, knowing that J is 0.108 divided by our number of compounding periods per year, which is 1. So it comes out with the same interest rate as the nominal rate, and that will only occur when our interest rate is compounded annually, okay? Because that means it's compounded at the same frequency of our nominal interest rate. So we're not dividing it out into smaller interest payments throughout the year. Our last piece that we need is our number of compounding periods, our total number of compounding periods, that's N. Okay? Remember, that's equal to the number of years in the term multiplied by our number of compounding periods per year. In this case, we're not just given number of years, we're given 7 years and 5 months. So we have to convert those months to years, okay, and then add them together. So we have 5 months divided by 12. Remember, there's 12 months in a year. Okay, that gives us 0.416 as a repeating decimal years. And then remember, we have an additional 7 years. So we add our 7 years, and we get that our investment is a total of 7.416 years. Okay. Putting those together to find N, we have our number of years, 7.416 years, or 666, I guess, if you want to write it as a repeating decimal, times 1, because our number of compounding periods per year is 1. It's compounded annually. So our value for N is 7.416, again, as a repeating decimal. So now we have all of our data, okay? We take all of these numbers now, we can simply substitute them into this formula here on the left, and we'll have our solution. So our future value is equal to our present value, $8,000, times 1 plus our periodic interest rate, 0.108. And that's raised to the exponent 7.416. Again, I'll just write it as a repeating decimal. If you multiply these out, you get a total value of $17,116.96. Okay? Again, you might have received a solution a little bit different than this. Okay, off by a couple cents here, maybe off by $1 or $2. That's okay. Okay, if you're looking for solutions in questions, okay, on a test, if it's multiple choice, make sure you look for that solution that you're really close to. Okay, if you got an answer of something like $17,596, that is just too far off from this solution. Okay, the reason your solution might be off by a couple dollars or a couple cents is because of rounding when it comes to doing these calculations. Okay, especially when you have something like a repeating decimal here. If you're carrying a lot of decimal places, you'll get a solution very close to mine. If you're carrying less decimal places, usually it's a little bit off from what I have here. Okay, so just remember to keep that in mind when you're looking at your solutions, especially on a test. Okay, so let's look at a second example. Again, just trying to reinforce these concepts for you. Determine the future value amount of $400 invested at 6% per annum, compounded quarterly for 3 years and 5 months. So once again, we're looking for the future value. Okay, so that means we go back to our formulas and say, okay, we have a formula for future value. It's equal to our present value times 1 plus our periodic interest rate to the exponent n. So again, we focus on our sidebar here. We don't know what our future value is. That's what we're trying to solve. What we do know is we know our present value. Okay, we're investing $400. So our present value is $400. So now we can start to work towards finding our other two items, our periodic rate of interest I and our total number of compounding periods n. So our periodic rate of interest I, remember it's equal to our nominal rate of interest J divided by our number of compounding periods per year M. So J, in this case our nominal interest rate, again given in the question, 6% per annum. Converting that to a decimal, remember we remove the percentage sign, divide by 100, so it's 6 divided by 100, which gives us 0.06. M, our number of compounding periods per year, again, it's given in the question. It's compounded quarterly. Okay, so when you see quarterly, all right, that means every 3 months. Okay, there's 12 months in a year, so quarterly is 4 compounding periods per year. If you're still getting used to these, okay, quarterly, annually, semi-annually, items like that, they will start to just come to you quickly as you do more and more of these questions. So with J and M, we can now calculate our periodic rate of interest, just substituting in our values. J is 0.06 divided by M, which is 4, and that comes out to 0.015. Okay. Our last piece we need is our total number of compounding periods N, and that's equal to our number of years multiplied by our number of compounding periods per year. So remember, just like our last question, okay, we have years and months. So we have to convert those months to years. So if we look at our formula, that means our number of years is 3 years plus we have 5 months out of a year. So remember 5 divided by 12, converting that to years because there's 12 months in a year. And that's being multiplied by our number of compounding periods per year, which is quarterly, so 4. Okay. If we add those up, 3 plus 5 over 12 gives us 3.416, again as a repeating decimal, multiplied by 4. So our value for n is 13.6, again as a repeating decimal. Your calculator will show it as 13.666, continuing on. So now we have all of our terms. We can simply substitute them into our equation and solve. So our future value is equal to our present value, $400, times 1 plus our periodic interest rate, 0.015, raised to the exponent, again, 13.6. Sorry, decimal's in the wrong spot. 13.6 as a repeating decimal. And if you multiply this out, you'll get an answer of $490.26. Okay? So that's just, again, using the same methods we did in the previous question. Okay, let's look at one more example. Charles took out a loan for $5,000 with interest at 7.75% per annum, compounded semi-annually, and it's repaid after 5 years and 10 months. So here we're going to find two items. A, how much Charles had to pay at the end of the term, and B, the interest that Charles paid on the loan. Okay, we're looking at, he took a loan out for $5,000, and he'll have to pay a certain amount back that's more than $5,000. So we want to look at what that interest is. Basically, how much did it cost Charles to take out that money? Okay, you can think of that in terms of mortgages. When you buy a home, okay, you're paying interest to the bank as part of your mortgage payments, and that is an amount that you're paying the bank so that they'll give you the money to buy a house. Okay, so let's look at this example. So we're starting with how much Charles had to pay at the end of the term. When you read end of the term, okay, that means we're looking for the future value. We're looking ahead to determine how much he'd have to pay. So we're starting with our future value formula once again. And that's equal to our present value times 1 plus our periodic rate of interest I to the exponent n. Once again, with my sidebar here, we don't know what the future value is. That's what we're trying to determine. We do know the present value because we know what we started with, okay, which was a $5,000 loan. So our present value is $5,000. Our periodic rate of interest I is equal to our nominal rate of interest divided by our number of compounding periods per year. Our nominal rate of interest is given in the question, J, 7.75%. Now remember, we have to convert that to a decimal. So we do that by taking 7.75, removing the percentage sign, dividing by 100, and you get 0.0775. Okay? When you have exact numbers like this, don't round that. Don't try and round it to 3 decimals like 0.078. Okay? Don't do that, because if you do that, every time you do more and more rounding like that, your answer will change compared to the answer that I come up with. Okay? So make sure when you can to carry more decimal places so your answer is closer to mine. So next we need our number of compounding periods per year, M. It's given as semi-annually. Okay? Semi-annually meaning twice per year. So our value for M is 2. So with these, we can calculate our periodic interest rate, okay, I, which is equal to 0.0775 divided by 2, okay, because we're compounded semi-annually. That gives us 0.03875. So our last piece of the puzzle that we need here is our number of compounding periods, our total number of compounding periods, N. Okay, so N, remember, it's equal to the number of years of our investment multiplied by our number of compounding periods per year. So remember, in this question, we have 5 years and 10 months. So we have to convert the 10 months to years. So N is equal to 5 years plus 10 months divided by 12, because we have to convert those months to years. And that's multiplied by our value for M, which is 2, because it's semi-annually. Okay, if we multiply this out, we get that N is 11.6, again, as a repeating decimal. And you're going to see a lot of repeating decimals when we do these styles of questions, okay? And that's just, the nature of, converting months especially, okay? Because there's 12 months in a year, and it doesn't necessarily divide to an even number, okay? So you're going to see a lot of repeating decimals. With all this data, we have everything we need, so now we can simply substitute in our values here. So our future value is equal to our present value, $5,000, times 1 plus our periodic rate of interest, 0.03875. And that's raised to the exponent 11.6, again as a repeating decimal. If you multiply this out, you get $7,791.10. So you can see in almost 6 years, Charles needed this $5,000 today, but when he goes to pay the loan back, he will have paid a total of almost $7,800, right? So the difference between these two numbers is how much it costs Charles for this loan. What that interest that he pays is how much it costs him. So for part B, the interest is simply your future value minus your present value. Okay, so $7,791.10 minus the present value. What was the amount of money you were loaned, which was $5,000? So subtracting these, you get $2,791.10. Okay, so you can see this cost an enormous amount of money, okay, relative to what the loan was to achieve it now. Okay, this is just something that I know a lot of you will look out for when you're doing car loans, when you're doing loans for some toys that you might want to purchase, whether it's a Sea-Doo or a snowmobile, or maybe an RV or a motorhome or something like that. Okay, all of that borrowing money comes at a cost. Okay, in some instances higher than others. Okay, now let's take this a step further. Okay, I want to look at some applications where maybe your interest rate changes after a period in time. Okay, so that's common for savings accounts. Okay, it's common for mortgages when we get later on the calculations, where your interest rate doesn't necessarily stay the same for the entirety of your investment. Okay, and basically what you're going to see is the easiest way to do these is to approach them by taking them in terms of a timeline. Okay, determining multiple points may be future value calculations at intermediate points to find your solution. So for this example, we have a deposit of $2,000 and it's earning interest at 6% per annum compounded monthly for 4 years. At that time, the interest rate changes to 7% compounded quarterly instead of monthly. So what I want you to determine is what is the value of the deposit, A, at the end of 4 years before the interest rate changes, and B, 3 years after the interest rate changes, meaning a total of 7 years from now. So if you are looking at this question, starting to figure it out, you can pause it right now. Okay, pause this video, try the question yourself, and then watch the solution if you like. You'll notice that on this slide, I haven't posted the solution down here. It's actually on the next slide because this usually takes more than one slide for me to write. So it's a perfect opportunity for you to try this question and then compare your solution to mine. Okay? So let's look at part A. Okay, at the end of the 4 years before the interest rate change, okay, what is that value? And I'm going to start this by just drawing a timeline. Okay, so we're here today at time 0. And we've put a deposit in for $2,000. Okay, that's our present value today. For part A, we're looking at 4 years later. Okay, so 1 year, 2 years, 3 years, 4 years. Okay, what is the value at that point? So what is the future value here? I'll use the subscript 4, okay, just to denote, year 4. So what is that future value here? That is what we're looking for in part A. For part B, what we're looking is further into the future, 3 years after, what is that value? So we're looking year 5, year 6, year 7. Okay, so in part B, we're looking for what is the future value in 7 years. Now, the way to accomplish this is remember our formula is our future value is equal to our present value times 1 plus the periodic interest rate to the exponent n. The difference here is our values are not going to be the same. Our interest rate's different, our compounding periods are different, our time frames are different. So you need to do 2 separate calculations. first, you need to take your money today, $2,000, and find the future value at year 4. You're then going to take that future value and we're going to pretend that we're 4 years in the future. So now that future value becomes your present value for your next question. Okay, so your present value there becomes what the future value was, because we're transporting ourselves 4 years in the future. For our second calculation, we're then going to find the future value 3 years ahead from that. Okay, that allows us to use, for the first calculation, this interest rate compounded monthly for 4 years. For the second calculation, okay, it allows us to use the new interest rate, 7%, compounded quarterly for 3 years. Okay, so you're going to see me do this a lot in questions where you break them up into these pieces. Okay, so I just want to explain my thought process before we just dive into now answering both part A and part B. Now that we kind of have a grasp or a path that we're going to take to solve this. Okay, so for A, we're going to, again, use our little sidebar here. And we don't know our future value. Okay, we're looking for the future value at year 4. We know our present value is $2,000. That's today. That's our loan. And we also know some other features. Okay, we know our nominal interest rate for this first period of 4 years is 6%. Which, remember, converting to a decimal is 6 divided by 100, removing the percentage sign, which is 0.06. For M, okay, it's compounded monthly, meaning that M is 12. So our periodic rate of interest, I, is equal to J divided by M, which is 0.06 divided by 12, which is 0.005. So our last piece for part A is we need our total number of compounding periods. Well, it's given as 4 years. Okay, we don't have any other conversion to make. So we have 4 years multiplied by 12 compounding periods per year, gives us a value of N of 48. So this allows us to find our first future value. So our future value, again, at year 4 is equal to our present value, $2,000, times 1 plus our periodic interest rate, 0.005, raised to the exponent 48. Probably hear my calculator doing it in the background with you at the same time. So our future value is equal to $2,540.98. Okay, so remember, that's our value here. Okay, that's our future value here. Okay, so that's if we were sitting here today at time 0. 4 years from now, that's how much it's worth. For part B, we now have to move 4 years in the future. So we're sitting right here now. Okay, so that value of $2,540.98 is no longer our future value. Okay, that's our present value today. If we're talking about being there at 4 years from now. So our present value for our second calculation is the $2,540.98. Now what we're going to do is find the future value 3 years after that. Okay, because if we start at this time period, we can use the new interest rate, which is 7%. Okay, so once again, we're now going to go from this point at year 4 into the future to year 7. Okay, so switching to our other slide again, just so we can fit all of this. Remember, okay, we started at time 0 with $2,000. We're now 4 years in the future, and we have $2,540.98. And we're trying to get to year 7, okay, because we have a different interest rate, a different amount of compounding periods per year. So we're trying to find the future value at year 7. So once again, for part B, okay, our future value at year 7 is equal to our present value. And now I'm using a subscript 4 just to denote year number 4. Okay, you don't have to use these subscripts. I just find it easier to help differentiate in our timeline. And that's multiplied by 1 plus our periodic interest rate I, all raised to the exponent n. So once again, we'll do our sidebar here. Our present value is equal to our present value at year 4, $2,540.98. We know our nominal interest rate now is the interest rate that happens in 4 years, what it changed to, which in this case is 7%. Converting that to a decimal, remember you take 7 divided by 100, removing the percentage sign, which is equal to 0.07. Our number of compounding periods per year is quarterly. Okay, so that means M is 4, 4 times a year. So our periodic interest rate I is equal to J divided by M, which is 0.07 divided by 4, or 0.0175. Our last calculation is for N. And in this case, we're looking at 3 years after the interest rate changes. So our number of years is 3. And remember, our number of compounding periods per year, M, changes for this second period. It's quarterly. So it's now 3 times 4. So our value for N comes out as 12. So now again, we have everything we need to solve this. So we simply substitute it in. Our future value at year 7 is equal to our present value at year 4, $2,540.98, times 1 plus our periodic interest rate, 0.0175, to the exponent 12. Multiplying this out, we get our future value at year 7 is $3,129.06. Okay, so this calculation is the same thing that we've done in our previous examples. We just have to think about it a little differently and do 2 separate calculations in order to take into account any changes to our interest rate or our compounding period, or both. Okay, it could happen as long as they happen at the same period in time. Okay, let's look at a second example of this. So we have a debt of $500 and it accumulates interest at 8% per annum compounded quarterly from April 1st, 2017 to July 1st, 2018, and then 9% per annum compounded monthly thereafter. Determine the accumulated value of the debt on December 1st, 2019. Once again, okay, now we're talking in months. So it's helpful to start this with a timeline. Okay, so I'll start with our timeline here. Okay, so right now is April 1st, 2017. Okay, we're going to go to 2018, April 1st. Okay, still has not accumulated. Okay, we'll call it April 1st, 2018. Okay, then I'll keep going. April 1st, 2019. Okay, again, I'm going just in 1 year increments here to make it a little bit simpler. And we see here that, neither one of our dates follows that. We have a July in 2018, okay, which is somewhere in here. And December 2019, which is after April, we'll call it somewhere here. Okay, so I'm just showing you kind of how I build this timeline. Okay, a lot of times I find it easier to start in 1 year increments and then kind of place these dates, okay, if they don't neatly fit in this timeline, kind of approximately where they need to be. So we need to do 2 calculations here. Okay, our first calculation starts with a present value today of $500, and it goes all the way until the interest rate here changes, okay, which is July 1st, 2018. So we're going to do a future value calculation here first. Okay, I'll change that to blue just so you can see what I mean. Then after that point, it's a different interest rate compounded monthly. So we do a second calculation, moving ourselves once again into the future to this point in time. We do a second calculation to find the future value at this final point, December 1st, 2019. So we're doing two calculations again. So our first calculation will be from today to July 1st, 2018. Once again, we're finding a future value. So we have our future value is equal to our present value times 1 plus the periodic rate of interest raised to the exponent n. Again, doing a sidebar here, we know our present value is what we started with for our debt, $500. Our nominal rate of interest for this period is 8%. Remember, converting to a decimal is 8 divided by 100, removing the percentage sign, which is 0.08. Our number of compounding periods per year, m, it's given that it's compounded quarterly for this period in time, so m is 4. So we can find our periodic rate of interest, I, okay, that's equal to j divided by m, which is 0.08 divided by 4, which is 0.02. So our last piece of the puzzle here is to find our total number of compounding periods, n. And that's equal to our number of years times our number of compounding periods per year. So we know we're going from April 1st, 2017 to April 1st, 2018. That's 1 year. And then we're going April 1st, and we just count the months. April to May, May to June, June to July. So that's 3 more months. So n is equal to 1 year plus the additional 3 months. Again, we have to convert those to years by dividing by 12. And that's multiplied by our number of compounding periods per year, which is 4. If you add these together, you get 1.25 multiplied by 4 gives us a value of 5. Okay, so now we can find our first future value calculation. So that future value is equal to our present value, $500, times 1 plus our periodic rate of interest, 0.02, raised to the exponent 5. Okay, multiplying that out, you get our future value is $552.04. Okay, so that is our future value here, okay, at July 1st, $552.04. So now, again, we transport ourselves to the future here, to July 1st, 2018, and we note we start at this point. So now this value of $552.04 is our present value for our next calculation. Right? Our next calculation will be from that point in time, July 1st, 2018 to December 1st, 2019. So again, we start with our formula. So our future value is equal to our present value times 1 plus the periodic rate of interest raised to the exponent n. Now remember, our periodic rate of interest and our total number of compounding periods are all going to be different here. Okay? So we start with our periodic rate of interest. We need our nominal rate of interest and our number of compounding periods per year. So our nominal rate of interest has now changed. It's 9%. Converting that to a decimal is 9 divided by 100, removing the percentage sign, which is 0.09. Our number of compounding periods per year, we're now compounding monthly. So m is 12. So finding our periodic rate of interest I, it's J divided by M, okay, which is 0.09 divided by 12, which is 0.0075. Okay, again, don't, just because there's more decimal places here, don't round it, especially when it's an exact number like that. So our last item we need, we actually have two of them. I didn't write it, but our present value in this case is the number we have as of July 1st, 2018, $552.04. Our last piece we need here is our value of N. Okay, and now we're going from July 1st, 2018 to July 1st, 2019. That's 1 year. And then we're going from July to August, September, October, November, and December. Okay, so that's 5 months. So our value of N is 1 year plus those additional 5 months, converting them to years by dividing by 12, and then multiplying by our number of compounding periods per year, which is 12. Okay, multiplying that out, we get a value of N of 17. Okay. Substituting all of these values in now, our future value, now we're looking at our future value for December 1st, 2019, is equal to our present value, $552.04, times 1 plus our periodic rate of interest, 0.0075, all to the exponent 17. Okay, multiplying this out, we get our future value is equal to $626.81. Okay, so again, we just did two calculations here when the interest rate changes to find our final value here at the end. So I had a second page here. Now we managed to fit it all in the previous slide, but you can see the solution here. So if you had paused to follow along by coming to this slide, you would see the same solution that I came up with. Okay. If you printed these out, you may need this second slide as well, just for doing your solutions. Okay, so we're going to look at another application here. In this case, we're not going to look at an instance where we have changes in interest rates. What we're going to look at here is what if we have additional deposits, okay? So this is a very common scenario for you. You start off by putting a certain amount in your savings account. It's earning interest. And then maybe every month or every 3 months or every 6 months, you add additional money to it. Okay, so we're starting to look at slightly more complicated examples each time, kind of inching closer and closer to what you would see as real life examples. Okay, so let's look at our example here. Midland Credit Union showed that a client deposited $2,000 into an investment plan account on February 1st, 2015. The client invested an additional $1,900 on February 1st, 2016, and $1,700 on February 1st, 2019. What is the value of their investment on August 1st, 2025, if the plan earns an interest rate of 7% per annum, compounded semi-annually? So you're going to see that we have to do more calculations here, right? But we always can start by constructing a timeline just to figure out how all of these events unfold. So looking at this timeline, okay, so we started today, okay, I'll call it Feb 2015 with $2,000. Then exactly a year from today, Feb 1st, 2016, okay, we added an additional $1,900. Okay, so we're going to have our $2,000 that earned interest to this point plus our $1,900. Then we're going to go once again. Okay, we have 2017, 2018, 2019. Okay, 1, 2, 3. Okay, periods where we have another $1,700 added. Okay. And then we're looking further on in the future. Again, I ran out of room for space. August 2025. And we want to know what the future value is here. So while this looks complicated, again, we're just going to do 3 separate future value calculations. Okay. In this case, we don't have to actually change any of our interest rates or compounding frequency. The only thing that changes is the amount of money at the start, the present value in each calculation, and our total number of compounding periods N for that term. Okay, so what we do is we start with $2,000. We're going to find the future value of $2,000 here. Okay, then at that point in time, we're going to add $1,900 to that. That becomes our present value at that point in time in 2016. Once again, we'll do another future value calculation to bring us to 2019. So we'll have a future value here. We'll take that number, add an additional $1,700 to it. That becomes our present value at that point in 2019. And we do a third future value calculation to find August 2025. Okay, so make sure you use a timeline effectively here. Okay, these calculations, when you look at it, it's 3 calculations, the same formula all 3 times. Okay, you just have to understand how this timeline works. Okay, so we're going to start with our formula. Our future value is equal to our present value times 1 plus our periodic rate of interest, all to the exponent n. Okay, so for our first calculation, our present value is $2,000. Our nominal rate of interest, which is the case for all items in this question, is 7%, which is 7 divided by 100, removing the percentage sign, or 0.07. Our number of compounding periods per year, again, the same for all of our questions, is 2 because it's semi-annually. So our periodic rate of interest I is J divided by M, which is 0.07 divided by 2, which gives us 0.035. Okay. Our last piece here is our number of compounding periods. Again, for N, it's equal to our number of years. For our first calculation, it's only 1 year, February 1st, 2015 to February 1st, 2016, times our number of compounding periods per year, which is 2. So our value for our first calculation is 2. I'm going to call that N1. Okay, now that number is the only one that changes. Our periodic rate of interest does not change. Okay, so I'm going to actually do all 3 calculations of N, okay, right now, okay, just so you can understand the differences. So N2 is for the second time frame here, from February 1st, 2016 to February 1st, 2019, which is a period of 3 years, again times 2 compounding periods per year, which gives us 6. For our third one, it's a little bit different because we have to figure it out all the way to August. So we're going 2019 to 2020, 2021, 22, 23, 24, and 25. Okay, so to February 1st, 2025 for N3, okay, that's 6 years. Plus, remember we're going February to March, April, May, June, July, and August. That's 6 months, okay? Again, divided by 12 months in a year. You'll see that that turns out to be semi-annually. That's multiplied by, again, our number of compounding periods per year, which doesn't change. In this case, it is 2. Multiplying this out, we get our third value of N of 13. Okay, that is for our final calculation here. Okay, I'll kind of denote them in colors here on the side so you can see. Okay, do purple for the first one, green for the second one, and this orange for the third one. Okay, so that's the only item that changes other than our present value for each. Okay, because remember, we're adding to our investment. All right. So I want to show you, again, I'm going to try and do it all on one slide. I do have a second slide here, but I want to show you it just so you understand how the numbers progress here. So our first future value calculation is equal to our present value today, $2,000, times 1 plus our periodic rate of interest, 0.035, and that's the exponent n. For our first period, again, the one in purple, which if you remember was 2. Okay? So you can probably hear me doing the numbers at the same time. So multiplying this out, future value for our first calculation is $2,142.45. Okay? So that is at this point here. Okay? So at that point, our initial investment is worth $2,142.45. So now we add another $1,900. So now picture we're at 2016. Our present value for this second calculation is the amount of money we have so far, $2,142.45, plus the additional money that we're adding, which is $1,900. That puts us at $4,042.45. So now we can do our second calculation to take that amount of money, right, and translate it to our next period where we add money, February 2019. So if we do that, our future value is equal to our present value, $4,042.45, times 1 plus, again, our periodic interest rate did not change, 0.035. But our total number of compounding periods changed. For this one, remember in green, it was 6 because we went 3 years into the future. So that's raised to the exponent 6. Multiplying that out, our future value at our second point is $4,969.20. Okay, so that is at this point here. Okay, now at that point, which is now 4 years from when we started, we're adding an additional $1,700. So again, I'll change to another color. Our present value for the third calculation is the amount of money we have, $4,969.20, plus the additional $1,700 we're adding. Okay, that puts our account at $6,669.20. Okay, now we can do our final calculation all the way to August of 2025. So our future value for our third one is equal to our present value, $6,669.20, times 1 plus our periodic rate of interest, 0.035. It did not change. Raised to the exponent 13 this time. Remember, because we did our last calculation for n. Okay, because we're going 6.5 years into the future. So if you calculate this out, you get our future value at the final point in time to be $10,430.34. Okay, so you can see here that all I did was progress to each period in time where something changed. In this case, the amount of money in our account was changing because we were adding money. In our previous examples, the interest rate that was available to us changed. Okay? The methods, vary a little bit, but again, if you follow the timeline, you'll see that it's the same formula just used repeatedly. Okay, so again, you can see I usually do this on 2 slides. I chose to do it on 1 just to show you how that progressed. Okay. So that was all I had for this lesson. It's just a long video for you. I apologize for that, but it's a lot of practical information to cover to start this course. These concepts are going to be critical for you doing well, especially through the first 4 units of this course. Okay. If you have any questions, please send me a message on Teams or send me an email. Thanks, everybody.